Okay, so today we want to find the average value of a function and the mean value theorem for definite integrals. Objectives, you want to find the same thing that's over there, right? Average value of a function and to apply the mean value theorem for definite integrals. This is not in your book. It should be. It is definitely on the test. So you're not going to find this anywhere in there to help you out. Be sure you take great notes on this because these are on every single AP exam. All right, let's get going. First of all, what's an average? Okay, hopefully you had time to kind of think about that for just a second. And then how do you find it? Most of the time people say, well, an average is a mean. But what's a mean? And, you know, what will it, you know, it's kind of that middle number, but it's not a median. That type of thing. If you look it up, it says it's a mean. If you look at in the dictionary. So if you look at mean, it says it's an average. So they kind of assume that you know what you're doing. So when you're doing how you find it, you know that you would add up if you were given a list of numbers and you wanted to find the average of those numbers, then you would just add them all up. And divide by how many numbers there are, in this case 6. And that would give you your average. Okay, well then what's the average value of a function going to be? I mean, I'm looking at a nice little curve that goes like this maybe. And if I'm talking about, sorry, I should have dotted this one over here from A to B. And if I'm talking about an average value of a function, then that would mean what little value, what is my average y value in through there? Well, yeah, how are you going to find that average y value? Probably we would think to do like f at x1 plus f at x2 plus f at x3. Or because that is going to be too long to write, because there are infinitely many dots here and I could never come up with all of them, we would probably write limit as n goes to infinity of the sum. Whoop, sorry y'all, I'm trying to write at the wrong angle so that the thing will pick up my voice, and I'm not doing a very good job. Okay, f at x of I. That would probably be how we would add them all together. But you still have to do what? Well, you still have to divide by however many there are. How many are there? I mean, infinitely many between there. So what are we going to do to find the average value of a function? Okay, well, let's go back and let's think about this right here. Okay, we want to be thinking about that right there. That right there is awfully close to something that we have been using. Okay, what have we been using? We have learned to rewrite that summation with a delta x behind it as an integral. But if I'm multiplying that sum, I equals 1 to n of f at x of I, limit as n goes to infinity. If that's how I add them together, and I want to rewrite it as an integral, and so I have to multiply by delta x, then that would mean I would also have to divide by delta x, right? And what is delta x? Generally b minus a over n. In this case, we're going to look at it as just that b minus a, because that's going to take care of finding the average. That's going to divide that out, and it's going to be, this is going to add them all up, and then this is going to divide by how many there are, because that's the distance, isn't it? Okay? So, if f is integrable on the closed interval from a to b, needs to be closed, cannot be open, then its average or mean value on that closed interval is average value of f, that's how you read that, equals 1 over b minus a times the integral from a to b of f of x dx. This part, let me change the colors here so you can see, this part adds it all up. This part divides by however many there are. So when it says find the average value of f of x on 4 minus x squared on the closed interval from 0 to 3, then you would have your average value of f. And some books do average of f like that. Some books even do f average like this. So, there's different notations, but I think you can kind of get the point there. Equals, in this case, 1 over 3 minus 0, integral from 0 to 3 of 4 minus x squared. Okay, so sorry, y'all. The Coach Carpenter interrupted and knocked on my door, which was very nice to visit with him for a moment. And the room was empty, and he was wondering who I was talking to. So, anyway, there is your integral. And so, therefore, you've got 1/3, and when you integrate that, you've got 4x minus x cubed over 3, going from 0 to 3. So you have 1/3. And when you plug in your 3, you're going to end up with 12 minus 9 from the first little bit, and then, of course, minus 0 from the last little bit. And so you should end up on that with 1. All right, so that's your average value of f of x. That means that's the average y value. If you're looking at 4 minus x squared on this, like this, and you're going from 0 to 3, see if I can make this a little bit better here. 1, 2, 3, we're close there. And I've got all of these y values going right down in through here. My average y value is at 1. Okay? Right there. Okay? That means this area right here, this area right here, okay? Then I've got those equal parts there. That's going to be my average y value out of that. I'm going to show you a little bit more about what that means here in just a minute. First of all, let's see if we can figure out where this happens. And this is going to happen wherever your function equals 1, right? Okay, where your f of x equals 1. So when you start to put it in here, you're going to have x squared equals 3 going through to solve, so x is plus or minus the square root of 3. Of course, we put our plus or minus, right? But in this case, since I'm going from 0 to 3, the positive square root of 3 is the only one that matters. So x is going to be about equal to 1.7. I'm sure there's a couple more decimal places there, but I don't have those memorized. So that's what we're looking at. With x is about 1.7, it's going to give you that right there. And so that's what happens. This area up here, this area down here, those are going to be about the same at that point. You've got that average value. Now here's the cool thing. I'll just wait and show you the picture. Okay, if f is continuous on that closed interval AB, then at some point C in AB, f at C equals the 1 over b minus a. That C value is what we just found on that last question right before. We found that point where this average value right here occurs. Okay? The value of C must be in the given interval. We marked out our negative square root of 3 because it wasn't in the given interval. Okay? So we need to know what is C, okay, and what does f at C represent? Okay, C is the x value where the average y value exists. Okay. Now remember that average y value is the average value of the function. Okay, average y value is the average value of the function. Okay, f at C is the average value function. Okay? You could also say it is your average height. Okay? Out of all of those little dots, that's your average height. Now, it still has a little bit more special meaning. We're getting to it. Just kind of be patient with me as we develop this. If I rewrite the formula as f at c, and then I multiply both sides from up here, if I multiply both sides by the b minus a, so that those would cancel like that, then, okay, that's where I get this formula right here. So what does that mean? Well, I know what this means, right? That's the area under the curve, true? Integral from a to b, f of x dx, x my area under the curve. So what is this right here? Well, if we just said that f at c was your average height, and b minus a is your width of your interval, then doesn't height times width, isn't that going to give us the area of a rectangle? So is the area under a curve a rectangle? Well, not necessarily, right? Because that could be something funny like this. Okay, well, let's move on and see if we can still get this. Make sure we understand. Okay, I'm reminding you of something before I show you this. Okay, we have two different mean value theorems. You have a mean value theorem for derivatives. This one, hopefully we remember, because we do not want to get this confused with the one we're working on right now. Mean value theorem for derivatives, where the instantaneous rate of change is equal to the average rate of change, okay? We're going to give you probably something along the lines of like time right here and distance right here. And so then this is going to be your average velocity, and this right here would be your instantaneous velocity. All right? So we remember that. It gave us time and distance on our x and y axis, and we ended up with something different when we divided them. Distance over time gives me my velocity there. Whole different thing. If this did not come to your mind when you saw mean value theorem for derivatives, write it down again. It's got to be stuck in your brain. However, here's your mean value theorem for integrals. This formula right here, the one that we've been writing down, says that the average height of f for the area of the rectangle is equal to the area under the curve. So all of the yellow here that's under the curve is equal to that rectangle. When you moved that over and had f at c times b minus a, that's the area of this rectangle. There's your b minus a right there. Here's your f at c. That gives you the area of the rectangle. That is the same as the area under the curve. Okay, so that f at c gives you your average height on there, so that when you multiply by the width, the area of the rectangle is the same as the area under the curve. Now then your difference on this, okay, when you're reading these, they're both going to ask you for average. You've got to be able to figure out which average do I integrate or am I taking a derivative. Okay, so this is where the potential for confusion comes in. On this right here, generally, let's say that they give you time and velocity. Okay, if they ask you for the average velocity when they have given you time and velocity, that's when you're going to integrate. If they ask you, if I gave you distance up here, if I gave you, and they ask you for average distance when they gave you distance, that's when it's going to be an integral. Because what you're doing on this formula right here is when you integrate, you know, velocity and time, you're getting, I'm going to take this away just for a second so you can kind of follow what I'm doing. If I integrate velocity and time, then right here I'm going to be getting distance, right? Because that's what we've said, that area under the curve is always the distance that you're going. So if I integrate my function that's done in terms of velocity and time, then I'm going to get distance. But if I then divide that distance by my difference in time, this piece right here, that means I've got distance over time again. And so that's going to give me my average velocity. If you're getting back the same thing that it gave you, I know I'm saying this a gazillion times, that's when you use integrals. If it is wanting you to do something completely different, it gives you two different things and it wants this, that's a derivative. If we have questions, please let me know in class. I'm going to move on quick here. Okay, so I have y equals secant x, tangent x from 0 to pi over 3. We're going to run through this real quick. F of c equals 1 over pi over 3 minus 0 integral from 0 to pi over 3 of secant x tangent x dx. And I'm going to let y'all go from there. I'm going to tell you, work through it, see what you get. Your answer should be 3 over pi. Double check and make sure that it is. Okay? And then this one right here I want us to work in class. All right, so we'll work that one in class, and then we should be good to go. You'll have your assignment, which is going to be your average value worksheet. Okay, I will talk to y'all later. Bye.